Algebras. Welcome to your Chapter 5, Lesson 3 notes. We are going to talk about solving systems of linear equations by elimination today. Okay, so the last one we looked at, we were solving by substitution, meaning we were getting one variable alone, and that expression that we had it equal to was substituted in for another variable in the other equation. Well, this time, the way that our equations look is actually going to be a little bit different. We're going to line up our variables, line up our equal sign, line up our number on the other side. And we're actually going to add the two equations together. And what this will do is we will purposefully cancel out a variable. It will leave us with an equation that has one variable in it. So we have that answer, and then we'll use that answer to help us find the other variable by substitution. So we'll use substitution for the second variable this time. But for the first variable, we're going to eliminate one of the two from the whole deal. Okay? So you'll notice that my two equations that I'm going to use for this linear system are actually lined up vertically, so over each other. The x's are lined up over each other. The y's are lined up over each other. The equal signs are lined up over each other. The numbers are lined up over each other. If you look at the y's, the number in front of this y is a positive 1. The number in front of this y is a negative 1. What happens when you add 1 and negative 1? You get 0. So what I'm doing on purpose is I'm adding y and negative y so that I get 0 y. And when I have 0 y's, I don't have to write y as my variable anymore because I don't have any. But I do still have x's left. But now that I have a single variable involved, I know exactly how to get that variable alone by algebra. So that's the whole point of the elimination method. Line those variables up vertically. Line those variables up vertically. Line the equal signs up vertically. Line the numbers up vertically. Everything has to be in its spot. Then you can add the two equations together. All right. So again, look, I get my answer for x. Now I take this answer for x and I plug it back into one of the original equations for x. I substitute back in, okay? And that is where the substitution method is still happening, is in that step when you know what one variable is equal to, you plug that in for the variable, finding the other, okay? So getting this as y is now my only variable involved, so now I get y alone. This is what I get. We still are finding the point where these two lines would meet. If I were to graph these two lines, the point they'd meet is 2, 0, comma between, parentheses around. That's my answer. Now I do go back and I check in both original equations. So we're going to do that process again. A few examples together, okay? But this is the procedure we'll use each time. So we'll start with making sure that our variables are all lined up, that our equal signs are all lined up, that our numbers are all lined up vertically, so one over the other. And if we look, we definitely have that to be the case. Okay, so that's the first step. The second step is that we need either the x's or the y's to, when they add up to 0. So you need to have the same number in front of the x's or the y's, but the opposite sign. I don't have the opposite sign, but I do have the same number in front of my x's. They both have a 1 in front, right? They don't have opposite signs though. So the way that I can force an opposite sign is to take one of the two equations and multiply it by negative 1. So I can force that to be a negative y, or excuse me, a negative x. And then that way, so I've got this negative x, I get this negative y equals negative 5. Now I've done it throughout, so I haven't changed the essence of the equations at all. So I've done it throughout. but I forced opposites. So now what I'm going to do is I'm just going to rewrite the other original equation. I don't change or manipulate this equation at all. Now that I have opposite signs in front of my y's, or excuse me, my x's, I can add them up. X minus x is 0 x's. Boom, gone. Let's try the y's now. 3y minus 1y is 2y. Bring down your equal sign. 13 minus 5 is 8. And now if you want to get y alone, what's the opposite of multiplying by 2? Divide both sides by 2. We get y equals 4. So there's one variable that I know. So that one variable I know is what's going to go in place of y in one of the two equations. It doesn't matter which, so I'm going to pick what I find to be the easier of the two. And I think the second equation before I manipulated it was easier. So now what I'm going to do is I'm going to replace y with 4 in that equation. So x plus 4 equals 5. Now to get x alone, I just subtract 4 from both sides. I get x equals 1. So my point that satisfies both of these equations, if I were to graph them in the coordinate plane, is 1, 4 in parentheses. Let's check that by rewriting both original equations and plugging back in. So x plus 3y equals 13. Got it. X is 1 plus 3 times 4 should multiply together to give me something that adds to 1 and gets 13. And thankfully, 3 times 4 is 12, and 1 plus 12 is 13. So that first check works. Now, the second check is going to look real familiar because it's actually the equation I used to find my second variable. So I'll plug 1 plus 4 back in, and of course, we do already know that 1 plus 4 equals 5, so we're good. Okay. A lot of people like the elimination method better. I know just for lines, I do, because you get to line them up, add them up, right? It's nice. Getting rid of one of the variables by opposites. Additive inverse. Speaking of, let's look at number 2. Okay. Well, first of all, the first thing I noticed about number 2 is it's A and B, not X and Y. When we make our point, it's still going to be alphabetical. Okay. Second thing I notice about this set of equations, is I don't even have the same number in front of either variable. They're lined up vertically, sure. A's are lined up, B's are lined up, equal sign number, good. But I don't have the same number in front of either variable. What could I do to one of those? Like up here, I actually didn't have opposite signs, so I multiplied my second equation by -1. Could I do something similar here? For sure. Okay. I notice in the middle with the B's, I've already got a -3b down here. Got a positive b here. If I multiplied this by 3, 3b minus 3b would be 0b. And that's my goal. That's what I want. So if I want to multiply this by 3, I just have to multiply them all by 3. So if I do that, let's multiply all these by 3. Then I've manipulated the equation to get something I want, but I haven't changed its essence. 3 times 13 is 39, by the way. So now I'm going to bring the second equation that I'm not going to change at all over. Okay, and I'm going to add these two things up. Because now, if I add 3b minus 3b, I get 0b. And that was the goal. So add the rest. 15a plus 4a is 19a. And 39 plus 18 is 57. So now, to get a all by itself, I just divide both sides by 19. And just a heads up if you don't believe me, right? 57, oops, go away. 57 divided by 19 is going to be 3. Just checking, right? Why have it if you're not going to use it? There's my value for A. Let's take this value for A, substitute it back into one of the two original equations, doesn't matter which, and then get out our B. So B is kind of already alone in the first equation, right? It's not alone on one side of the equal sign, but at least it's alone coefficient wise. So how about I plug back into that one? So I'm going to rewrite 5a plus b equals 13. And what I'll do is I'll replace a with 3. So 5 times 3 plus b equals 13. Well, 5 times 3 is 15 plus b equals 13. To get b all by itself, I subtract 15 from both sides. I get b equals -2. So that means that my point, if I'm creating my coordinate point, would just be alphabetical, is 3, -2 in parentheses, separated with a comma. And then that's what I'm going to use to plug back into the original equations. So again, the originals, not the manipulated. So 5a plus b equals 13. And this one will feel very familiar because we just used this one in order to get our second variable. So yeah, this one is going to be 13, right? That one checks, but got to check in both. So 4a minus 3b equals 18. 3 times -2, right? So 4 times 3 is 12, and -3 times -2 is +6. I get 18. 18 equals 18. 12 plus 6 is 18, so it works in both. Okay? There we go. So far, so good. All right. So last one that we'll do together. Variables lined up, equal signs lined up, numbers lined up. No coefficients the same. And in fact, I don't have any coefficients, like I don't have any variables alone that I could just multiply by one number. If I multiplied all these guys by 2, I'm not going to get anything that matches down here, right? So I guess I'm going to have to multiply both equations by something. So pick either the x's or the y's. It really doesn't matter which, but pick one of your two variables to cancel, okay? I'm going to pick the y's to cancel just because. Why not? Oh, get it? So I see that I've got 2y on the top one, 3y on the bottom one. I need them to be opposite signs. They're not right now. And I need them to give me the same coefficient. So you know what? If I multiply the top equation by 3, I'll get 6y. And I need the opposite sign down here. So if I multiply the bottom equation by -2, I'll get -6y. So that's what I'm going to choose to do, okay? And again, when you go to do this on your own, it doesn't matter which of your variables you pick to do the canceling, but pick one and follow through. So 3 times 7x is 21x. 3 times 2y is plus 6y in the middle. And on the other side of the equal sign, 3 times 5 is 15. Now, the opposite sign goes down here because I want different signs in the y's. Now, if the y's were already different signs, I wouldn't need to make this negative as well. I would just need the 2. But they also aren't opposite signs. So everything needed to change here. So -2 times 2x is -4x. -2 times 3y is -6y. There it is, the opposite signs, right? And then -2 times 16. Well, 16 times 2, you guys know that, right? Sometimes yes, sometimes no, right? There we go. So -32 because we're negative. Hey, use that graphing calculator. That's why you got it. Now I'm going to add these two equations up, and it forces a cancel of the 6y minus 6y. 0 y's are left. Now let's do the x's. So 21x minus 4x, so we get 17x. Bring down your equal sign. And just in case you don't believe me, 15 minus 32, so it's a -32, is -17. So now to get x alone, divide both sides by its coefficient, which happens to be +17. I get x equals -1. So that's my answer for my first variable. So let's substitute that back into one of the two original equations. Again, doesn't matter which, and honestly, one isn't really easier than the other because they all have coefficients. So let's pick the first one. 7x plus 2y equals 5. I'm going to substitute in x is -1. So I get -7 plus 2y equals 5. And now what I'll do, because I've already got my variables right here, I'll add 7 to both sides. I get 2y equals 12. Now divide both sides by 2 to get y equals 6. So I've got my x, I've got my y. That is a coordinate point of -1, 6. Again, create that coordinate point, check in both equations. So write the originals, not the manipulated, because if you did something wrong manipulating, it'll show up in your checks of the originals. So 7x plus 2y equals 5. Replace x with -1. Replace y with 6. And this one is the one that we just did to find the second equation. So this is the one that's kind of, it feels like, oh, I just did this. Yes, you did, but you still have to make sure that you double check in both. So got this one done. And then second one is 2x plus 3y equals 16. So 2 times -1 plus 3 times 6 equals 16. I get -2 plus 18. And yes, 18 minus 2 is 16. So there it is. You can probably see that one setup of the equation lends itself to elimination, and one setup of the equations right at the get-go lends itself to substitution. And so that's the last thing I want to discuss with you. Here are some pairs of systems. What's the most appropriate, probably the quickest method to use to solve? If you have a variable that is alone on one side of the equal sign, it's substitution. So here, I already have y equals 3x. I already know what y is equal to. So this lends itself to substitution. Okay, do you see any others in here that lend themselves to substitution already because of the setup of one of the two equations? Y equals x minus 2. It's already alone. It's lending itself to substitution. So that would be the method to use to solve that system. Now, when we look at this one, we can see A's lined up, B's lined up, equal sign lined up, numbers lined up. That is for sure elimination. Right? Now, in this one, I argue either, right? Because you could either add s to both sides to get r alone. That could be substitution. Or just switch the s and the y in one of the two equations. Just switch them around with their signs. Now you've got elimination. So this one, I argue either. Because one quick switch gets you into either mode. And that's kind of the point that I'm making here with all this is if they're already set up for something, do that something. But if you've got to do the manipulation, pick the method you like better. If you like elimination method better, fine. Switch the r and the s around in the first equation, boom, you got elimination. If you like substitution better, fine. Add the s in both sides in the second equation, boom, you got substitution. So this is going to be up to you, and you're going to know which one with your practice. So when you're practicing this on your homework on your own, you're going to figure out real quick which one you are more wired to do better. Okay? Again, if you need me, you know how to find me. But this has been your Chapter 5, Lesson 3 notes using the elimination method to solve a system of linear equations. All right? Good luck, guys. Let me know if you need anything. Bye.